In this video, I'll introduce you to solving separable differential equations. Let's first take a look at what a differentiable equation looks like that we can separate. You'll typically see it defined in terms of dy dx, or it could be f prime of x or y prime, and that's going to be equal to the product of two functions, one in terms of x and one in terms of y. Now, there are several different ways people go about separating them and approaching them. I like to use the definition of the differential to solve these. And once we use this, we'll look to move the y terms to one side with respect to y and the x terms to one side with respect to x. And then we'll be able to integrate. There'll be a constant value, that's that, don't forget the plus c, and then we'll be able to solve it. When you have initial value problems, they'll give you an initial condition where you're able to solve for that missing constant. Let's take a look at a few examples. In our first example, this may be something you recognize. It's dy dx equals negative x over y. If not, at the end of this, you will. First thing we're going to do is I will write down my definition. It'll be dy equals, and then I just replace dy dx with the definition of dy dx for this particular problem, which is negative x over y dx. From here, we're going to look to move the y terms to one side, so naturally we'll multiply both sides by y, and we're left with y dy equals negative x dx. I could have moved the negative, but I tend to leave constants and negatives on the right-hand side to make the y term easier to work with when I'm integrating. Now I'll look to integrate both sides, so I'll just throw my integral symbol on there to show my process. In integrating y, we have 1/2 y squared. Integrating negative x, we have negative 1/2 x squared. And this is where I'm going to put my constant. Some people might have two constants, one on each side, but they would combine to be just one constant, so we can leave it like that. At this point, I have two options. I can try to recognize my equation and solve it. Many times I'll actually solve for the y value. In solving for the y value here, I would have y squared equals, multiplying by 2, would give me negative x squared plus 2c. Now, c and 2c are just two different constants. So along the way, I usually like to mark it as c1, c2 to show the changes. Some people don't show this. I feel it's necessary to show how I'm changing these values. My next step, we will put up here. I would square root both sides. Now realize in square rooting, I would have plus or minus the square root of negative x squared. I could put plus 2c, or I'm just going to put c sub 1 for a new constant. And my initial condition would allow me to choose whether it's positive or negative and solve for the constant, because realize in these solutions they're going to be continuous over their domain, so I can't choose plus or minus, and they will be functions as well. So that's where we can leave it. Now again, some people may have recognized that equation there. Had I moved the x term over, I would have had 1/2 x squared plus 1/2 y squared equaling c. And multiplying by 2, I would have x squared plus y squared equals some other constant. I can say 2c. Some may recognize this as the equation of a circle. All right, on to example 2. And example 2 is a very common example that comes up. That's why I have a little template drawn out here. It says dy dx equals blank y. When you see this, you're going to want to recognize this is an exponential growth problem because it's very common. But let's just go ahead and go through the steps as usual. So we'll have dy equaling our dy dx, which is negative 0.01 y, and then we have dx. Now there's not much to separate here. I do need to get the y term to the left-hand side, so I will divide both sides by y, leaving me with 1 over y dy equaling negative 0.01 dx. I'm going to go ahead and integrate both sides. And in integrating 1 over y, you should recognize that as ln absolute value of y because of the domain restrictions. And that's going to equal negative 0.01x. And again, we have plus c. In solving for this, we would exponentiate both sides. So when I exponentiate both sides, that leaves me with the absolute value of y equaling e to the negative 0.01x plus c. Now at this point, some people might use exponent rules to simplify this, and we'll do that in a moment. So I need to take care of this absolute value. So we should know if it's the absolute value of y, that means y is equal to plus or minus. Now this is where I'm going to use some exponent rules about this plus c with a base of e. So we're going to want to rewrite this as e to the c times e to the negative 0.01x. Not necessary for many people, but what I want you to recognize is plus or minus e to the c is just some constant. So when I rewrite the solution to this problem, it's going to be y equals, now I'm going to put a, and then I'll have e to the negative 0.01x. And my initial value will solve for that a value. And so again, just realize that that a is just equal to plus or minus e to the c. And again, the initial value will help us solve for that. So this is your solution. Many people will just look at the question initially, the dy dx equals negative 0.01y, and know immediately what the answer is because there's lots of connections and they are not a coincidence. It will happen each time. So this negative 0.01 is over here as what we'll call our k value, and it will be of the form e to the kx. Problem number 3. Problem number 3, again, same approach. This one looks a little trickier for many people, but again, let's go ahead and write dy equaling, and we'll write down our dy dx, which in this case is xy squared plus x, and then we have dx. Throw some parentheses around there to show that it was actually substituted in. Now this one's a little tricky to separate my x from my y, so I have to realize I need to factor this one. So when I factor this one, I'm going to have x is common to both, leaving me with y squared plus 1. I still have my dx, and over here we have our dy. And now I'm able to separate my x and my y functions. So we need to write it as a product. So here is the first piece, here is the second piece. So that's something to look for, rewriting it as a product of a function in terms of x and a separate one in terms of y. So we'll go ahead and divide that y squared plus 1 over. That leaves us with 1 over y squared plus 1 dy equaling x dx. So now you're going to need to recall some of your integrals. So I need you to recognize where does 1 over y squared plus 1 come from. So some of you may remember that that is the arctan of y. This can also be written as the inverse tan. I like to use arctan because that -1 notation sometimes gets lost on people. And integrating x, we're left with 1/2 x squared plus some constant. So to solve for this, we just need to take the tangent of both sides. So we are left with y equals the tangent of 1/2 x squared plus c. And again, very important, any initial value will help us take care of the condition of where this function actually lies.